Hey, welcome back. This lecture is going to be on the idea of optimizing the basic disjoint set structure we've already looked at. We've seen last time the basic implementations of union and of find, and we talked before that about why that was really the only two functions we were really concerned with for the most part. And what we're going to be doing now is talking about ways in which we might speed things up. So last time we had talked about this basic idea, where our union, we had said for the moment we're going to make two assumptions, and one of them would be that we always pass in pointers to the roots, to union, and the second assumption was that we could always get a pointer to our node. So if I want to do a find on 6, I can easily get a pointer to 6 called x, or if I want to merge, say, 1 and this tree here, I can easily get pointers to 7 and 8, and I would be passing in pointers to 7 and 8 in that structure. And so we said in order to union two sets, you would simply point one to the other, because they each have this pointer on them. And these pointers for these would have been null, so I should probably draw those in as well. And for find, all that would be happening would be that you'd be given a pointer to some node, say 5 or 8 or 6. And if you had a pointer to 6, for example, you would set some temporary to there, and then you just basically say as long as the pointer off this node is not null, you move up to whatever it points to. And so 6's pointer is not null, so you move up to 5. 5's pointer is not null, you move up to 1. 1's pointer is null, so that's where you'd leave the while loop, and you'd return that pointer, which is now 1. And you could have used x as well, but we used a temporary and kept x where it was. There may be some reason for that later on, as we'll see. So that said, we mentioned last time then that your basic running times here for these are, well, your union is clearly always going to be constant time. There's only one pointer involved, one pointer assignment. And the find could vary. The time that find's going to run in depends on how long the path is that you search. And so, if you're searching up a very long path, find will take a while. If you're searching up a shorter path, if you start maybe more in the middle of the tree, or if your trees aren't that deep to begin with, then you have a shorter time. And so we had said basically that your times for your basic implementations, for your basic implementation, basically have union being constant time, and find in the worst case is order n, and find in the average case, where we say on the average these trees might be logarithmic in depth on the average. But in the worst case, you could have one long linear tree of all the nodes. And so that would be the worst case. And so what we want to do is improve upon this. And there's going to be two methods we use to improve upon this. The first is going to be to have unions run in a somewhat better way. And then the second will be that finds can actually sort of be redone a bit as well. So look at the idea behind union first. And the idea behind union, if we're going to do a sort of looking at two trees here, is I can say, well, what if I have this tree, and I have here, say, 7, that points to null, and here I have 4, and here I have 3, and here I have 2. And let's say this is our tree B, and then we also have some tree A, 6, 8, and 1, and let's say that's A. So now, what we've set up to this point is when you want to do a union of A and B, you simply would point B to A. But that doesn't have to be what we do. And in fact, in this case, we might not want that to be what we do, because the problem here is that by pointing B to A, we're making things, in a sense, longer. And we can see the results of that if we look at the most extreme case. What if I had B was some long linear chain, and your subtree A was simply one node? You're going to approach the worst case in this regard by saying, well, if I point B to A, I'm creating a still longer linear chain. Where if I was able to point A to B instead, at least it has something that reasonably looks like a tree here. I have a linear chain, but then there'd be two, this node and then that node, the node pointing to by A, would both be pointing to that top node. So I'd have, this connection would be what I might prefer to make, and say, well, now this node and this node both point up to that parent B. And that would make things a little bit better because now the root would have stayed where it is, and all of these nodes would have continued to have their same depth instead of now increasing by 1. The way we would get these linear chains, the way we'd build them, would be to say, take one of two things. Take a very long tree, very deep tree, and point it to some smaller tree. And that's exactly what we are doing in this sort of top dotted line here. We're saying, take this tree, which is of depth 4, and instead of having it be pointed to, have it point to A instead, and while we keep adding to this linear chain. And that's going to be the only way to build these linear chains, would be if we keep taking deep trees and putting them to smaller trees, like a one-node tree or that kind of thing. If we were to instead make a somewhat more intelligent choice and say, let's examine the two trees, instead of just blindly saying always point B to A, let's examine the two trees. And let's think to ourselves, well, if I somehow knew a certain property about the tree, I could maybe perhaps decide pointing the tree to one direction or the other is better. And one example might be height. You might decide that, well, it's best to say that the tree of smaller height should really be pointing to the tree of larger height instead of the other way around. And that would tend to keep the height smaller. And we could have done the same thing here, where I could have said, well, what I really want is for A to point to B, because B's got larger height, and so if A points to B, that will keep the height of the overall height of the tree smaller. Where if B points to A, now we're going to be increasing the overall height of the resultant tree. We could also have done this by size, where I say, B has more nodes than A, and so by pointing B to A, that now is causing problems that might not occur if I was to point A to B instead. And we could have trees such as those two, where B has both greater size and greater height than A. You may also have had a situation like this, 7, 4, 3, 2, and there's 4 nodes, and then A might have looked like this, where we have 0, 1, and 8, 9. So it could be the case that one tree has more nodes, the other tree has greater height. There are going to be advantages to both strategies, and we'll talk about them in a little bit. But the point is that we could make intelligent union choices, and based on evaluating the particular trees, could say, well, I'll do this evaluation, and I'll decide, well, these two trees have particular sizes, and I'll point the smaller size tree to the larger size tree, or I'll point the smaller height tree to the larger height tree. As opposed to just doing the blind, set the second to point to the first, which is what we've been doing so far. This is just sort of the naive implementation, the basic one, where we always say, well, the second tree points to the first. B points to A. And now what we could add a union is some means of saying, well, instead let's evaluate the properties of this tree and point the first to the second or the second to the first, depending on which one makes more sense. And as we said, there's going to be advantages to doing this based on height or by size, so we'll look at both ideas, and then we'll talk about which one has an advantage where. But basically, this is known as a smart union procedure. Smart union because we're making more intelligent union choices rather than just blindly pointing the second tree to the first one no matter what. And so there are two types of smart union. We can make our decisions based on the size of the trees, or we can make our decisions based on the height of the trees. And we'll look at both. Now, what we don't want to do when we talk about making our decision based on the size of the tree or the height of the tree, having to recalculate these heights or sizes would be a pain. When we've got, say, a tree like this, I don't have any children pointers downwards. If you give me a pointer to 7, I have no easy way of figuring out the depth of the tree, because I have no easy way of finding out what the children of 7 are, or what the children of 6 are in this example, for example, when there's many children. So the only thing I really have available to me is to look up every possible key do a find on all of them and find which key pointed to which key out of the keys that ended up pointing to B, which one took the longest. And that would sort of be the only way we go about counting the height. And we certainly don't want to do that, looking up all the keys and figuring out which ones are in the set B out of all our keys, and then figuring out which one of those took the longest to look up. That's going to kind of give us some hint as to the height of B. But it's, even if that number is accurate enough for our purposes, it's going to take a while to find that height. And we still would like union to run in constant time. And so rather than recalculating the heights or the sizes every time we need them, the sizes would be a little easier because we could just say, well, how many things when you did a find on them resulted in B, or how many things when you did a find on them resulted in A. Where a height, you'd have to also be able to know the running time or keep track of how many links you traversed or something like that, in addition to knowing how many just ended up at B. But if we were keeping track of this value as we went along, as we made these trees larger and larger through more unions, if we were keeping track of the size of the height, we wouldn't need to go through and do all this work and figure it out each time. And we don't want to do that extra work refiguring it out because it'll take too long. But if we've kept the size or the height all along, then it might be a lot easier to deal with. And so that's what we're going to do. We're going to assume that if we keep track of the size or height, and we'll show how, if we keep track of the size of this height each time, then what we'll be able to do is we'll have to, of course, modify things with each union, but we'll always have that value there to read. And so we don't need to recalculate and redo this work over and over again. It'll be done once. And of course, changed as we do unions, but for each individual tree, we'll have found out its own height or size just once. And so then that will be significantly less work than having to recalculate the height every single time you need a union, which will involve sort of traversing over the same trees and subtrees over and over again. So what we'll have here is a new value, a new uptree node. Up to this point, we have here our key, and if we're going to have an info associated with the key, here goes my watch. If we're going to have the info associated with the key, then we'd have that there too. So we sort of said, this was our sort of uptree node last time, where we had just the pointer and the key and perhaps the info as well. And so in addition to those three values, if we're going to have the key and the info, here we can also build in the size or height into that cell. So in other words, we'll have an extra cell in the uptree node now that will not just hold your key and maybe your info and your pointer to the parent, but also an extra field to hold the size or height. Now, there are some interesting times in the language when these, in certain languages, when these could be considered to be the same cell. And what the TAs go over will be sort of an implementation that sort of gets at that, where your pointer and your size value end up sort of, in a sense, being held, or exactly being held in the same place, and there's a way to distinguish between them. So that will sometimes be possible, depending on your exact situation and the language you're using, that you can have your size or your pointer stored in the same place. And we somehow know, if you can tell it's a size, then you know you don't have a pointer or it's a root pointer, because the top level nodes, the root nodes of these trees, could simply point to null. So you could have some way of perhaps saying, if it's a size or height, then we don't have a pointer and you'd assume the pointer is null. If you have a pointer that's not null, then you have no size or height. Because all we really need to do is store the size or height at the roots. So for example, if I'm going to store the height of this, well, the height is 3, I would store a 3 at the root. And if I want to store the height of this, I can store a 2 at the root. With these other nodes, it doesn't really matter. What matters is to say this is a smaller height tree and that's a larger height tree. I don't really need to worry about the sizes of these other nodes anymore. They're sort of buried in the tree, and all I'm going to be doing is basically saying, well, when it comes time to union these two, and I've got pointers to their roots, what I'm essentially saying is, well, I can have 3, I can look at the heights of both of them because I have pointers to both the roots. And so if I have the overall height stored at the roots, everything's okay. And so that'll be the concept here. Because I need the height or size only at the roots, it's possible to sort of have these two pieces of memory overlap and say, well, when I store a pointer, I don't need a size. And where I would need a size, I would know my pointer's null. And so if possible, if the language allows it and if circumstances allow it, you could get away with having the same memory cell being used for your pointer and your size or height. And like I said, the TAs will go over something that sort of does that kind of thing in a way. But that will be that. We can have them separate, and we'll treat them separate for now, but you could have the same value used for both the pointer and the size if need be, because we don't need sizes anywhere else except where the root pointer would be null. So let's look at union by size first. And if we're going to deal with two trees here, and let's say this one's smaller, here we have 4 pointing to null, and we have 7 and 5. And then maybe here we have 6 pointing to null, and 8, and 3, and 1. And here we have a size of 4, and here we have a size of 3. And so basically we want to take the tree on the left and point it to the larger tree. And what might happen would be then, or what should happen would be, you want to store 7 for the larger tree. If we're going to point one of these to the other, we'd say, well, here's now 4 pointing to 6. And then 6 has 8 pointing to it, and 3, and 1, and this would be null. And what I want now is to say, well, 6 is the root of a tree that holds 7 nodes. So I have, here I have a tree of 3 nodes, and there I have a tree of 4 nodes, and the combined thing would be a tree of 7 nodes. And so the way to handle this is, well, first thing we need to do is sort of evaluate what the sizes are. So here I have union. Say void. As before, I have a node pointer A and a node pointer B. And what I'll do now is I'll say, well, let me read the size fields of A and B. And so instead of just right away saying B pointer equals A, I can start out with a conditional. And I can say if the size of A is greater than or equal to size of B, as we see here. Or I'm sorry, in this case, if this is A and this is B, that's not the case. But in general, I'm saying if let's say this tree is A and that one's B, then in that case the size of A would be greater than or equal to the size of B. And if that's the case, if the one on the right was A and the one on the left was B, then what you'd want to do is to say, well, then I'd be pointing B to A. And so you can go ahead and say, ultimately, this is what you'll do. You'll say B pointer equals A. You also want to add the size values. And you probably want to add them beforehand rather than saying B pointer equals I and then add their size values. Because as I mentioned before, if you happen to have a situation where you can overlap your size and your pointer, well, you're going to want to read, you're going to want to read your size field before you change it into a pointer. So if this 2 is a size, and then eventually we have to lose that size because we want to activate the pointer to that node, well, we're going to lose the 2. So it's important to read the size value before you get rid of it if you happen to be using the same memory cell for both the size and the pointer. And like I said, the TAs will go over an example that sort of does that. But because of that, if that's going to be your situation, you're going to want to make sure you read that size before you change your size field to a pointer field and lose that size. And so what happens then is we can say here that I want A of size, we can say plus equals B of size, which means A of size equals A of size plus B of size. Plus equals just means add this to what's there already. So it's when you're adding to a value, then you're going to write the result in the value you're adding to. Hopefully you're familiar with that terminology, but if not, that's what it means. X plus equals Y simply means X equals X plus Y. And the other option here would be now, if this is the case, if we reach the else case here, then it means B size is greater than A size. In that case, we do exactly the opposite. Here then we say B size plus equals A size, and then A pointer equals B. And there's your union based on size here. We're saying figure out which tree is bigger. The top case is where whatever A points to is bigger. The bottom case is where whatever B points to is bigger. And then if A is bigger, then you add B's size to A size and point B to A. If B is the bigger tree, you add A's size to B's size and point A to B. So it's exactly the same situation in both cases, just A and B switched. And of course, if the two are equal, we don't care which way you go. If you have two trees both of size 4, then either one could point to the other. We're just saying by default, we'll have the equal cases handled with B pointing to A. And so that's basically what we did here. If this had been tree A and this had been tree B, then we notice B's size is greater than A's. We would have added the two sizes together and stored it inside B's field and then pointed A to B. And now that node 4 is further down the tree instead of being a root, it doesn't really need a size field. It has one, but it doesn't need one. And so we'll never be reading that size field again. We only care about the size at the root. Notice, of course, this is still constant time. It's now a tiny bit more expensive than it was before because now we have a comparison and an addition in addition to a pointer set. But still, it's basically all we have. We have one comparison that lands us at that line or at that line, and then we have an addition either way and a pointer set either way. And the setting of the pointer we had before, the addition and the comparison are new. But certainly an addition and a comparison, neither of them takes very long, and so this is still constant time. Find, of course, still works the same way. It's simply traversing up the structure as it did before. But now we will presumably be keeping the structures from getting too close to the linear collection, one long linear collection of elements. Presumably things will remain a little bit more balanced, and we'll discuss that shortly. So we expect by rewriting union in this way, it'll keep the trees a bit more balanced, and find will tend to run a little bit faster. Now, as far as union by height goes, we might notice here that if I have two trees, say here's 4, that's null, and here's 3, and if I have 6 and 7 and 9, and that's null. If I have those two trees and I point 4 to 6, then what happens here is that the overall tree is still height 2. This is a height 1 tree, that's a height 2 tree, and we can even sort of put those labels on again. So here's height 2, and here's height 1. And if I point 4 to 6, because 4's got the lower height, the overall tree still remains of height 2. More generally, if I have some tree that has height h plus 1, and then I have some tree whose height is less than or equal to h, if I'm going to point the smaller tree to the large one, I'm adding exactly one extra link. So if the height here from the deepest leaf to the old root is less than or equal to h, and now I've added one link to get to the new root, then the deepest path from the deepest leaf here to the new root along this path is going to be less than or equal to h plus 1. And that's what this overall height was already. Or in other words, what this means is if we have two trees that we're doing a union on, and the height of one is smaller than the height of the other, then the union cannot change the height. And this is pretty much your general description of that. Since this tree, that the height's defined by the path length from the deepest leaf to the root, and now we've added only one extra edge to that path, going from the old root to the new root in one edge. And so if this was definitely smaller than the height of the overall tree you're merging into, then the resultant path here can be at most equal. And so the overall height wouldn't change. But on the other hand, if you had two equal trees, here you have h plus 1, and here you have h plus 1. And if you're pointing one root to the other, along this path now, you have h plus 2. If the deepest leaf up to the old root was h plus 1, now you've added one edge to it. Now the path from the deepest leaf to the new root is going to be h plus 2, and that's greater than the h plus 1 you'd have here. And so the new height's defined by whatever the tree that did the pointing to, its deepest path is now it determines the new height, which is h plus 2. So those are your two possibilities for union by height. If the trees are different, the height actually doesn't change. If the trees are identical in height, that's when the height value would change. And so we can write union by height and say, well, here's void, and we say union node star A, node star B. And again, we can start out with a comparison. I can start out by saying if it turns out that A height is greater than or equal to B height, then that case here will eventually end in saying, I should say B pointer is equal to A. And if it's not the case, if it turns out that B height is greater than the A height, should have got a flub there on the slide. If the B height is greater than the A height, then you simply point A pointer to B. We haven't finished this yet, but at its core, that's what union looks like for union by size, because most operations don't have any need to change the height. For most times, we'll be having the smaller height tree point to the larger height tree, and so then we're done. Which means all we would need is the comparison to tell us which way to point, and then do that. If A was indeed greater than B, we would have done what we originally did in the basic implementation. If, on the other hand, B had a greater height than A, we'd point things the other way. And that, in its core, is all we need here, is just saying, well, there's no sizes to add every single time. We simply say point A to B or B to A, but one of the two will be what we want to do. And so we use a comparison to decide between them, and then have our pointer assignment. The only time when we need the height changing as well, unlike union by size, which had to do a size change every time, when you added two trees, they were the sum of both nodes, collections of nodes. The only time we need to worry about here is if it turns out that two heights are equal, not just greater than or equal, but specifically equal, then we can say that the height of A, in addition to pointing B to A, the height of A is added, is increased by 1. We could have just as well have put in this code down here instead. We could have said if A height is greater than B height, then point B to A, and then otherwise, and had this be the B is greater than or equal to A case, and then the equal down here. It's not really important which case handles the equal, so again, by default, we'll just say, well, the A, we'll do the same thing when they're equal as we will when A is greater than B. So we'll handle that. We'll point B to A if they're equal, rather than the other way around, but it doesn't really matter. But the idea here is, the only time we actually need to change the height is when not only if A is greater than or equal to B, will B point to A, but in addition, if it is equal, if the two heights are equal rather than A being greater, you also need to augment the height of A. That's what we saw down here. The overall height of the tree is increased by 1 if the two subtrees had been equal. If they were not equal, then the overall height stayed the same. So that's all we're saying here. We're saying if A's height is greater than B's height, either way, if A's height is greater than or equal to B's height, in both cases you'll be pointing B to A. But if, in addition, if it happens to be equal rather than greater than, you'll have to increase the height as well. And so, of course, this is constant time. You had your comparison. If the comparison's false, the only extra operation you have is a pointer assignment. If it's true, you'll have that pointer assignment plus one more conditional and a potential addition. So at the most, you have a condition, another condition, an addition, and a pointer assignment. That's just one more condition check than union by size, and that's still constant time. And so that's union by height there. And so as you can see, both the union by size and union by height aren't too complicated. They're just small changes of the basic code. But what they do manage to do for us is they'll guarantee now a worst case for find. Because you can imagine, consider a collection of nodes, say 8 nodes that are all in their own set to begin with. Sort of the worst case for us now, in a sense, in terms of doing union, is when the smart union wouldn't matter. If I was going to union 2 subtrees, A and B, before, I had basically 2 options, or 3 options. A and B could be identical in height or size. A could be greater than B, or B could be greater than A. Those were our 3 options. And in the old union, the worst thing that could happen would be, actually, let me go ahead and put something on the slide here. You had in the basic implementation, you could say that A was greater than B, A is equal to B, and A is less than B. And in the old union, when you always said B pointer equals A, then this was your worst case. Because if A was greater than B, in terms of height or size or whatever else, then B pointing to A is exactly what you would have wanted to do anyway. If A was equal to B, it didn't matter which one pointed to which one. And if A was less than B, that was the situation that caused long linear chains. When I was saying, take the larger tree and point it to the smaller one. Now what we have, when we do smart union, we still say if A is equal to B, we'll say that B pointer equals A. And if A is equal to B, then we'll say that B pointer equals A. But now, if A is less than B, smart union is telling us I can say A pointer equals B. So this is now a good case. And that's what smart union does for us. It takes this case that causes problems and says, I'll point things the other way, which makes not only is this a really good situation, but now this is a really good situation too, where smart union made a difference. Where smart union won't make a difference is if you had 2 tie trees. In that case, either way works just fine. So that's, in a sense, the worst situation we might run into. As long as we're always taking the larger tree and having the smaller one point to it, we'll be okay. And if we had gotten lucky, and that always happened before, everything would have been all right. If things were equal, then either choice would have been okay. We'd sort of, as long as the subtrees are always equal, the height continues to increase, and so on. And we've eliminated the really bad case of pointing large trees to small ones, and that sort of leaves this as now the slightly worse situation, where there are no decision to be made, no improvements. It's like, smart union doesn't really make any difference at all if A and B were equal. Or in other words, the tree will get larger faster when A and B are equal. We've already seen that's the only time the height can increase. And in terms of the size, the size, of course, increases no matter which way you do things. But in terms of the eventual heights that result, the two subtrees being equal sort of is the worst case there as well. And we can see then, basically what happens if we were to say, I'm going to do a union of 2 and 1. And I want to do a union of 3 and 4. And I want to do a union of 5 and 6. And I want to do a union of 7 and 8. And the distinguishing feature of each of those unions is that it's a tie, both in size and in height. And now what if I want to do a union of 1 and 3? Again, it's a tie. They're both size 2, height 1. And so if I'm going to do a union of 1 and 3, I end up with a tree that looks like this. And likewise, here I have 2 identical trees, both size 2, both height 1. So if I have here, do a union of those 2, I get this tree. And now again, if I do a union of 1 and 5, they're both size 4, height 2. They're both identical trees. And so I can say, let me do a union of 1 and 5, and I end up with a tree that looks like this, where here's 2, 3, 4, 5, 6, 7, and 8, which is a height 3 tree. 8 is the deepest node, 1, 2, 3 nodes to 1. And that's the worst case, or doing continual unions where we have a tie will be the worst case, because if we are doing continual unions and the two trees are different, we'll never be increasing the heights. The heights of these trees increase when we're doing constant ties. And as far as sizes go, then it's the same sort of concept. We're still trying to keep heights down, but as we'll talk about in a moment, with size issues, keeping more of the heights down. And there's no improvements to be made here either way. So this is the worst case for union by size and union by height, is when you're always doing ties. There's no advantages to be had. There's no way to say, hey, we'll point the smaller tree to the larger one and keep a lot of heights the same. We're increasing the heights of the same number of nodes either way. The tree height overall increases either way. And so if we have a whole bunch of ties, that's going to be the worst case. And in that case, this is by no means just a proof, it's just an example. But in that case, you have logarithmic, a tree of log height. It's not possible to get linear chains anymore, but you can get a tree of logarithmic height. And so now when you add in smart union into the mix, your union is still constant time. Your find now is worst case log n. The average case is very hard to analyze, and we're not going to do that. There's no clear what the average case would be, but the worst case is log n, and that's usually just that's where the analysis stops here, because the analysis isn't really clear for a average case once smart union is tossed in, or the result isn't clear. So we're not going to worry about that. Just focus on the worst case, and the worst case here is log n. Before that was the average case, now it's the worst case as well. By doing smart union, we assure ourselves of balanced up trees, and therefore we don't have long linear chains to search through. Now that said, the question is which one is better, and the answer is it depends what your goals are. If you're going to say we're going to do union by height, for example, if I have this tree and I have that tree, I can say by pointing this to here, if this is, say, my A and this is my B, by pointing the smaller height tree to the larger height tree, what we are doing is, actually, let me go ahead and add more nodes here so that the smaller height tree is a larger size tree. So let's go with those diagrams. And so by pointing the smaller height tree to the larger height tree, what we're doing is ensuring that the height doesn't change. And the height, of course, is based on the deepest path. Here we have a path of 2 to the root. Here, each of these is the path of 1. Now, when we do the union, that assures us that since it was a smaller and a larger tree, that the path to the root has remained as small as possible. And in this case, it hasn't changed. 2 of these nodes take 2 edges to get to the root. Now, all of these nodes take 2 edges to get to the root, to the node that was pointed to by B, and then to the new root pointed to by A. And so, union by height minimizes your worst case result. That is, it minimizes the worst case for find. It optimizes that. On the other hand, if we're going to do union by size on the exact same trees, we'd be pointing the second one to the first one, because there's 4 nodes there and there's 5 nodes here. And so we'd be saying point A to B. And the question is, why would we want to do that? And the answer is, well, notice here, in terms of how many nodes had their size increased, had their height increased, formerly when I did a find on this node or this node, it took me 2 edges. Or basically, I had to look at 3 pointers. This pointer up to here, then the middle node's pointer up to there, and then this would have been null before the union. So there were 3 pointers to look at there because it was a height 2 tree. Likewise, this took 2 pointers to look at, and the root only needed 1 pointer because you said, hey, the root's null, so then I know I'm at the root. Now that I've done this union, each of these now needs to look at 4 pointers. This pointer, this pointer, this pointer, and then B's null pointer. Likewise with that node and with that node. Or in other words, by pointing A to B, what has happened is every single node inside A, now we need, when we do a find on it, to look at one additional pointer. And likewise here, when I pointed B to A, whenever you did a lookup on any node in B, you had to look, now because of the union, you have to do one additional pointer lookup. You can't stop and say B is null, because B is not null. You'll follow B to A and then find out A is null. So in this case, each of doing a find on any of those nodes will now take one additional pointer to read. And in this case, doing a find on any of these nodes will require that you read one additional pointer than you had to before the union. And so what union by size is saying is increase the lookup times for the minimum number of nodes. Here, even though the overall height has been kept shorter, there have been 5 nodes whose height was increased, as opposed to 4 in this case. So basically, while union by height minimizes the worst case find result, union by size minimizes the expected case find result. We now have a height of 1, 2, 3. So the worst case leaf, which is these two here, are now, the time to look up those is increased from 2 to 3. And here we didn't have any leaf that took more than 2. So you might increase your worst case lookup. But what union by size will do is say, we're willing to say that certain nodes will take, the worst case will increase, as long as, for the most part, we have more nodes that don't increase than do. And so we're saying, yes, a small number of nodes are having their find time increased. And so the worst case does indeed go up by 1. But most nodes, the majority of the nodes stay the same. And so that's what we're worried about here. The expected case, the expected number of pointers you have to look at for find is going to be lower. If you add up the running times for all possible finds in all the nodes and then divide by the number of nodes, your sort of expected time for find is going to be shorter because more of the nodes stay the same than changed. And so that's the difference between the two. Union by height makes sure your overall height stays small, and so the worst case is minimized. Union by size will say, I'll allow my worst case to be a little worse as long as more nodes than not remain the same depth. Now the other thing we could handle, so that's smart union, and there's not going to really be any other way to handle unions to increase the running or improve the running time for find. Right now we're doing everything we can. We saw in this last picture, once I point 2 to 1, 2 is stuck pointing to 1. Or once I point 3 to 4, 4 is stuck pointing to 3. So if I had this situation, the ideal case, there's null, 2 points to 1, here's 3, 4 points to 3. If I'm going to union 1 and 3, what I had in the other slide was that I'd have 2 and 3 pointing to 1, 4 pointing to 3. Because I'm just pointing 3 to 1, and so that's what I get. When in reality, the best possible case would have been for all of them to be pointing directly to 1, where you have a root, and then all the other nodes in the tree point directly to that root. We don't have that here. And there's no good way to get it just by messing with union, because once union points 4 to 3, union has no idea that 4 exists after that. We're only dealing with roots, and we don't have any easy way to traverse down and find all the children. So when I point 3 to 1, our structure right now does not have any easy means of saying traverse downward to all my children, such as 4, which is the only child in this case, but in theory you could have many more children than that of 3. Traverse downward to all the children of 3 and point them all to 1 as well. We don't have that ability to do easily. We have to look up every value, see if it's part of set 3, and then point it to now 1 instead. And that's going to take a while, and union won't be constant time anymore. So because it's not easy to find out what points to 3, therefore when it comes time for 3 to point to something instead of continuing to be a root itself, we don't have any easy way of saying, oh, all those things that pointed to 3, they should point to 1 now. Because we don't know what pointed to 3, and we don't have any easy way of finding out what points to 3. So as far as keeping union constant time, we're pretty well stuck with what we've got. Smart union is nice, and it makes find run faster in the worst case. But there's still this restriction of once 4 points to 3, union can't do anything about that anymore. Now, as far as union's concerned, 4 will forever point to 3. And 3 could point to something new, but there's no way to go down and find 4 and have it point to 1 as well. And so union can give us, from these two, it can give us this. Union cannot, if it's going to remain constant time, from those two give us this. On the other hand, we'd certainly like to get that. And so the way we're going to achieve that is to go ahead and have a new optimization, which is going to be known as path compression. And path compression is going to be a long-term view of things. We're going to basically be saying the given tree as it exists will determine how long find takes. But what we can do is, as long as we do that find, we can improve things for the next lookup. So if I have here a structure that looks like this, say 1 is null, and I have here 10. For this, we won't worry about smart union for the moment. Here we have 2, and here we have 6, and 9, and 11, and 23, and 16, and say 12, and so on, whatever else we have. And let's say now you have a pointer to 11. Well, what I could do is say, what I eventually want to return is a pointer to 1. My find is going to send back to me a pointer to 1. Eventually I'll have temp, temp points to here. This is my x. And here I have temp, and then temp points to 9, and then temp points to 2, and then temp points to 1. And then we say, well, now 1's pointer is null, so we return 1. What if before we return 1, what we do is we say, well, now that I know what the root of this is, everything along the path from x to 1, I will point there. So, of course, 2 already points there, and 9 can be pointed there, and 11 could be pointed there. We can't get 23 or 16 because we can't traverse downward. But what we could say is everything along the path from, and we can even, just to make it clear what we're doing here, I can even draw that, which won't change anything, but we're saying here 11 will stop pointing to what it points to and point to the root instead. 9 will stop pointing to what it points to and point to the root instead. 2 will also point to the root. Of course, it did already. But in general, we're saying wherever we start, from that node up the path to the root, all the nodes we encounter will point directly to the root, giving us a new tree that looks like this, where I have here 1 and 10, and then here I have 2 and 6 and 3, and I have here 9 and 12, and I have 11, 16, and 23. And that's going to be, if we kind of look at it, how deep the nodes are, there's a lot of nodes that are pretty deep in the original tree. Now a lot of them are very much near the top. We still have a few really deep nodes, like 3, but for the most part, most nodes are closer to the top than they used to be, because 9 can now reach the root in 1 pointer rather than 2, and therefore so can 12. And 11 can now reach the root in 1 pointer rather than 3, and therefore 16 and 23 are now 2 shorter in their paths to the root as well. It used to take them 4 to get up to the root. Now it only takes them 2 to get up to the root. And so while that didn't improve the running time for this find, and in fact, since we had to go and set those pointers, it actually, in a sense, perhaps made it slightly worse, because you needed 2 passes up the tree instead of 1, so it's 2 times log n rather than 1 times log n. But what it does mean is that now the next time we do a find on 16, 23, 11, 12, or 9, it's going to be faster than it used to be. Faster than it would have been if we'd kept the tree like this. And so over the long term, if you do enough of those, you'll have a lot of values pointing directly to the root. Every one of these path compressions potentially speeds up the find time for many nodes with just a few pointer changes. And so one way we can code this is basically 2 passes up the tree. I'm going to redraw that exact same tree we had before. So here's 1, and the root is null. We have here 10, 2, 6, and 3, And we have here 9, 12, 11, 16, and 23. And let's go ahead and write find. We want to send back a node pointer. We have our x here. Let's say x points to 11. The first thing we can do is run that exact same loop we had before, where we say our original loop for find, where I can say you have some node pointer temp equals x, and then while temp pointer is not equal to null, then temp equals temp arrow pointer. But we're going to not return just yet, because of course we wanted to do the setting of the other pointers. So aside from the return temp statement, that was our code for find from before. And what that will do is position temp up here. And then what we can do is say, well, now I will create a few extra pointers. I'll say node pointer t2 also equals x, and we'll have a node pointer t3 as well. So we're going to say, well, I'll point t2, point t2 to where x points to, t3 I just haven't assigned yet. And what I want to do is basically point x, or point 11, point what t2 points to, up to the root. But by pointing it up to the root, by pointing 11's pointer up to the root, I lose 9. If I change this pointer now, I won't have a pointer to 9 anymore. It'll be hard to find it again. This is my direct pointer to it. Take that away, and now the only way I have to reach 9 is through the lookup structure. And so I want to save that first. And so we'll have a while loop here. We'll have a looping construct. And the first thing we're going to want to do in that loop is set t3 equal to t2's pointer. And so what we'll be doing here is saying whatever t2 points to, have t3 point to its parent. And we're going to fill out the while loop condition in a moment. Then I can say t2 pointer. Now that I've safely saved that, the variable can be overwritten. And that can equal temp. But the idea here is I save the value of t2 pointer in t3. I save the location of 9 in t3 so that I can change 11's pointer and lose the location of 9. And so I can say, well, now this gets changed. And 11's pointer points up to 1. And then now that that's done, now I say, well, now restore t2 to what t3 was saving for it. And so then what I'm saying in that case is I can change this pointer and say t2 points to wherever t3 was, and that cycle can then just repeat. We can then say basically move t3 up to point to 2, which is 9's pointer, and then make 9's pointer point to temp, and then move t2 up to 2. And this can be repeated over and over. Ultimately, the way this could stop, that we could stop a little bit earlier if we want to be ultra efficient, but I'll focus on making it clear at the moment. What we want to do is we want to say, well, we don't want to do this when t2 pointer is null. So we can say, as long as if t2 pointer is not null, that means t2 is not at the root. And that means we could go ahead and do this, and we can say, well, t2 is not at the root, so point t3 to the root, point 2's pointer to 1, and then move t2 to point to 1 also, which is what t3 pointed to. We could really have stopped that a node earlier and said, while t2 pointer is not equal to temp, and so I could have done, now instead of that, I could have said, while t2 pointer is not equal to temp, that will now, instead of waiting until t2's pointer is null, which meaning t2 is on the root, we can stop when t2's pointer is temp, meaning when I'm on a node that points to the root, I know it already points to the root. So we could have done either of those conditions. That shouldn't be taken as both of them. that should be taken as one or the other. If we check if T2 is equal to null, we'll go all the way up to the top of the tree, and that might be a little bit clearer, but we can actually stop the node before and say T2 pointer is equal to temp, and that's when we stop. And we continue as long as T2 pointer is not equal to temp. And that would save us the extra time of pointing 2 to 1, since 2 already points to 1. But the first condition might be a little easier to understand. The second one is sort of an optimized stop one case earlier deal. And so then once that's done, all you need to do is return temp. So this is the new part, and the earlier part and the return temp are exactly what we had before. This part is a retraversal up the tree to set everything one by one to the node 1. So now 11 will point to 1, 9 will point to 1, 2 still points to 1, and so everything from where we started up to the root node points to the root node, and that gives us the tree we drew earlier. And so that's path compression. And the idea then is that that improves things in the long term. Now we'll have what we can say is basically we still have the running times. Well, firstly, union, of course, has not changed at all, so this is still constant time. Find still potentially has a worst case of order log n. Of course, your best case has always been constant time. All we're saying now is we have more constant times due to path compression. And so what path compression will do is it'll say we didn't have fewer worst case situations because we're continually fixing the tree by making the height smaller, by pointing items to the root. And so we're tending to have more constant time situations now and fewer logarithmic situations. And so the actual bounds for find haven't changed. You can still have a log n tree if you do a bunch of union ties and don't do any finds. But we'll tend in practice to have more of them be constant time and fewer be log n. And you'll have, be speeding up values, and they'll get the running times will tend to be shorter. Now, this is assuming, of course, smart union and path compression together, and we'll talk about their interactions in just a moment as sort of the final thing we mention. But what it turns out then is if you have m operations and n elements in the universe, your total running time is going to be m log star n, worst case, which means the expected operation time is going to be order log star n. I'll explain what log star n means in just a moment. But basically what we're saying is if you do m elements, or m operations, if your universe is n elements, you have n different uptree nodes, and you do m of these operations, total of m unions and finds, this can be proven. The worst case time, if you add the time for all the operations up, the worst case time will be m times log star of n. So we're saying add up all the unions which we know are constant time, and all the finds, some of which can be log n, some of which can be constant, or anything in between. And it can be proven if you add up all those times, all the unions which we know the time for, and the finds which can vary, but we expect to be faster rather than slower most of the time, the total amount of time that takes is m log star n, or on the order of that. And so if that's the total time for all the operations, then, divided by m, and we say the expected case for one operation is log star n. Now, that doesn't mean every operation is log star n. We know the unions are going to be constant time all the time. They're always constant time. The finds could be as bad as log n and as good as constant time. So individual operations have varying times. What we're saying is if you add up all the operations, well, from a long-term view, each operation seems to take in about that much. Just like when we talked about the stack, and we said, well, you have a bunch of constant time pushes, but every once in a while there'll be a linear push because you have to increase the size of the array. From the long-term view, given how many operations you did and the number of amount of time the whole total mess of operations took, each operation appears to take constant time. And likewise here, if you add up all the constants and all the constants and log n's and everything in between, and divide by the total number of operations. Each one appears to take log star n time. Now, what is log star n? Well, we're saying if you take the log of the log of the log, blah, 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 the log of 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 n, you want to keep taking the logarithm until you're less than or equal to 1. The number of times you had to take the logarithm, that's I is equal to log star of n. And it turns out that this is a huge, huge, very short number. For example, consider the number 2 to the 6, 5, 5, 3, 6, which is an astronomically large number. Log base 2 of that is going to be 6, 5, 5, 3, 6, which is 2 to the 16. So log base 2 of that is 16, which is 2 to the 4. So log base 2 of that is 4, which is 2 squared. So log base of 2 is 2, and log base 2 of 2 is 1. So the logarithm 1, 2, 3, 4, 5 times. Meaning, of course, that the log star of 2 to the 6, 5, 5, 3, 6 is 5. This is a huge number, and the log star result is just 5. And so that's all we don't really need to worry about anything more than that. This is a not quite constant time, but darn near close to constant time for that reason. We're basically saying that this function grows so slowly that for any data set of any practical size, we're dealing with constant time here. And so that's why these are very nice. In practice, each operation for disjoint sets using these two takes nearly constant time. The last thing I want to mention very briefly is we have the notion here of if we use union by size along with path compression, there is no problem. Path compression does not affect union by size in any way. If you're using union by height along with path compression, path compression, since it can mess up the heights of the trees, you now have, in a sense, an estimated height instead of the actual height, because path compression has messed up the height. This is known as union by rank. I'm not going to require you to remember that term, but that's what this is called. And it turns out it's not a problem. You'd think that this is the problem, that path compression is messing up the heights of these trees, but in practice, the heights never get very big anyway because you're doing path compression and doing smart union. So it's not like you typically have, height trees that are of height, 20, and now suddenly you think the height is 5, and now that's a problem. In practice, putting path compression with union by height turns out to be okay, even though your height measures now are not always entirely accurate. Now it's just sort of the estimated height, and that, in practice, it's been shown to work fine. So even though you might think path compression interferes with union by height, really it doesn't, and you get the same benefits either way. So you can use both smart unions with path compression. And that's about it. So that's the disjoint set structure, and next time we will be talking about tries. See you then.